All right. But of course, if you overthrow me in the ride, then you'll never get any snowy stickers because I'll be dead. You know. So. Soon. It'll be like the third, starting with the third one, and then the fourth and fifth one will be involving that. But I'll show you other shortcuts that won't require you to memorize all the coordinates. We're going to learn the coordinates today. We're going to do the coordinates today. Stuff like that. Okay, so today we're going to be assigning coordinates to the unit circle. All right. And of course, we call this thing the unit circle because the circle has a radius of what? One unit. You know, a unit. Circle of radius units. All right. So if you look at your unit circle, right, we have quite the task because there's a lot of points on here, right? I think there's 17. Well, I guess 16 if you don't count the twice right here, right? So that's quite a bit, right? 16 coordinates to kind of come up with here. But we're going to focus first on finding the coordinates of the points here in the first quadrant. Okay, sorry, the points here in the first quadrant. And then we'll kind of use that to help us figure out the other remaining points. All right? So, general overview here, right? We have the it's not bad. All right, the unit circle there. All right, I'm not going to put all of our things in here, but we already know some of the coordinates of the unit circle, right? So, for example, here where we are at 0 degrees, 0 radians, or 2 pi radians, or 360 degrees, if you like, what would the coordinate of this point be again? 1, 0, right? Because we know this is a circle centered at the origin with a radius of 1. So we're exactly 1 away horizontally from the origin, so the coordinate would be 1, 0, right? It makes sense that that's the coordinate. Likewise, the coordinate up here at, what's the angle up here? 90 degrees, or in radians? Pi over 2. Okay, so this would be 0, 1. It's like, Mr. Wood, you can't ask us that. We spilled out all of our knowledge onto the quiz, and now it's all gone from our heads, right? No, but I'm going to do that anyway. Okay. What about this angle right here? 180, or in radians? Pi, and so the coordinate here, though, is going to be what? Negative 1, 0. Yeah, exactly right, because we're just, left 1 from the origin. And then what's this angle right down here? Okay, the coordinate will be 0, negative 1. What's the angle there? 270, or in radians? 3 over 2 pi, or 3 pi over 2. Yeah, however you want to say it there. Yep. Okay. So we know some of the angles. We know some of the coordinates of our angles on the unit circle already. But there's still 3 in quadrant 1, 3 in quadrant 2, quadrant 3 and quadrant 4. All those have 3 angles that we don't know their coordinates. So let's focus on the next angle that we come across here. So starting at 0, the next angle we come to is 30 degrees, or in radians? Pi over 6. Yes, so we'll get to that. So so this angle right here is pi over 6, or 60 degrees, Mr. Wood. 30 degrees. Okay, but yeah, I'm kind of like running out of space there. So what I'm going to do is I'll draw a bigger version of my... Let me just focus here on the first quadrant. So if you will, I'll just redraw that first quadrant. Okay, still have my axes. There's the origin right there. So here's my first quadrant. This might make it a little bit easier to see. Okay, like that. Okay, and again, the unit circle kind of goes more around that way, but I'm just focusing on that first quadrant there. Okay, and so again, there's again pi over 6, or 30 degrees, however you like it there. And our goal is to come up with an x and y coordinate for this point on our unit circle. All right. Well, remember, the x coordinate of a point is kind of like that horizontal distance that point is from the origin. So we need to come up with this horizontal distance. If I kind of drop down, we want to find this length right here, right? That gives us the x-coordinate. The y-coordinate is the vertical distance from, or the vertical, I guess kind of distance from the origin there. And so that would be like this coordinate, or this point right here, right, the side. That would be like our y. With these two measurements kind of drawn into our picture here, what kind of shape have we created? A triangle. It's a right triangle. Very good. And in fact, it's something, if you remember back from geometry, it's a special right triangle because it's a 30, and this would be 60, and that would be 90-degree angle right there, right? It's a 30, 60, 90 right triangle. It's special because it's half of an equilateral triangle, and so the sides have a particular kind of relationship. Okay, so let's now extract this triangle that we've made out here.
Mr. Wood, when does hypotenuse be 1?
So we're going to get to that, yes. How do you know the hypotenuse is going to be 1?
Because it's the radius.
Right. So the hypotenuse of this triangle right here will be a distance of 1 because it starts at the center of our circle and goes to the edge, right? This leg right here, well, we don't know its length, right? Because it starts at the center, but it doesn't go to the edge of our circle. And here, this height, this leg right here, it goes to the edge of the circle, but doesn't start at the origin. So we can't quite get those values. But we do know the hypotenuse will be 1. And we do know that this angle here, I'm just going to use the degree measure here just for now, is 30 degrees. And again, this is labeled as a y, this is labeled as an x. Okay. So let's say, for example, here that we wanted to find our x-coordinate. Okay. What trig ratio can we use here to help us solve for x? Yeah, so x is what in relationship to that 30-degree angle? Adjacent leg, right? And we know the hypotenuse, so we want the trig ratio that has adjacent and hypotenuse. Ca, C-A-H, right? That's cosine. So cosine of 30 degrees equals the adjacent leg over the hypotenuse, x over 1. Which then really just means that x is equal to the cosine of 30 degrees, right? X divided by 1 is just x. Okay? If you go to your calculators and you type in cosine of 30 degrees, I'll just give it to you if you don't want to type it in. It's going to be about 0.866, which is, pretty decent to know that. But precisely, it will be the square root of 3 over 2. Okay? And again, that comes from the relationships with the 30, 60, 90 right triangle and stuff like that. Okay, so our x-coordinate over here is root 3 over 2, as Joey said earlier. So questions on any of that right there? That gives us the x-coordinate now using the cosine. Okay, so then what if we wanted to find the y-coordinate? What trig ratio could we use there? Sine, right, exactly right. Sine of 30 degrees will now relate the opposite leg, y, to the hypotenuse 1. So sine of 30 is equal to y over 1, which means then y is just the sine of 30 degrees. And what is the sine of 30 degrees? It is 1/2, yes. Okay. And so, let me scoot that out. There we go. Zoom out just a little bit there. We get the coordinates for the point here on our unit circle. Root 3 over 2, comma 1/2. So yeah, we're gonna take advantage of that in just a second to then get the rest of the quadrants. But yes, in a sense, right? You might have to do like a negative or a positive. Right. One thing I am going to point out here that you maybe didn't talk about when you learned if you learned trigonometry last year or even in geometry too. One thing, and you talk about unit circle at least. One thing that I'm going to point out here that we will be seeing later in this class is an alternative way to graph points in the plane. Okay, so since elementary school, you guys have always used 2 numbers to locate a point in the coordinate plane, right? You used an x-coordinate and a y-coordinate. X told you how much to go left or right. Y told you how much to go up or down. But an alternative method that we're going to be using later in this class is called polar coordinate system. And the polar coordinate system still uses 2 numbers, but it uses those numbers in a different way. The first number is how much you rotate to get to the point from this axis, from the x-axis right here, how much you rotate, and the second number is how far from the origin you go in that direction. And that allows you to then locate any point in the coordinate plane, and it allows for some interesting graphs. So for example here, one way we can locate this point using our traditional method is to go right root 3 over 2 and up 1 over 2, right? Go right root 3 over 2 and then up 1/2. But another way to locate this point is to rotate 30 degrees and then go out, well, what's the distance from the origin to this point? 1. So another way to find this point is to rotate 30 degrees and then go 1 in the direction of that angle. Okay, that's called polar coordinates. Okay, and it results in some very interesting kind of graphs, something completely different. Okay, we fundamentally change how we locate things in the coordinate plane, and it can result in some interesting graphs and functions and things. But that's for a later part of this class. Something we have to worry about right now. Okay, so. Let's continue on then to our next angle. So we did 30 degrees and gave coordinates for this point. So what's the next angle we'll run across here? What's after 30? Well, 60, but before 60 and after 30? 45. Okay. So again, 45 degrees would be like right here. And same idea. Again, we want to find this x coordinate here. Again, this is 4 pi over 4 or 45 degrees there. Okay, we'll call this right here y. Okay, because that's again the height. And we're trying to find the coordinate of this point, blank, comma, blank. Okay. Now, what's special about this particular triangle? 45, 45, 90, and so therefore it will be by its sides, not equilateral.
Anything about triangles.
It's like
Two equal sides. What do you call a triangle with 2 equal sides? Isosceles. That's right. We heard it earlier, right? Okay. Okay. Isosceles is at least 2 equal sides. Every equilateral triangle is technically isosceles, I think, at least by the definition they give in the Common Core book. All right. So, yes, let's go ahead and again, let's extract this triangle out. What's the hypotenuse of this triangle? 1 again. Right, because we're going from the center to the edge of the circle there, and again, there's 45 degrees. Okay? So, let's say again we wanted to solve for that x coordinate. What trig function we want to use here to find x? Sine of 45 would give us x? Cosine of 45, right? Because cosine of 45 is the adjacent, okay, over the hypotenuse. Now, granted, Andrew, you weren't wrong because, right, if we use sine of 45, that would give us this side, and then because it's isosceles, these two are going to be the same. So you're not wrong, but...
I just said either one because I think that either one would be good.
Yeah, of course, yeah. You were just testing me. I got you.
Yeah, I just want to make sure you do.
Yeah, thanks. So cosine of 45 degrees, if you type in your calculator, you're going to get a decimal. It's approximately 707, is that what it is? Okay, but it's exactly root 2 over 2. Okay? And that one you can actually get pretty easily by, using Pythagorean theorem here. Since these two things are equal, you can call them both x if you wanted to, for example. X squared plus x squared is 2x squared. That's equal to 1. Divide both sides by 2, you get x squared equals 1/2. Square root both sides, you get x equals root 2 over 2 when you rationalize and stuff like that. All right. Sine of y, not sine of y, goodness gracious. Sine of 45 degrees, that would be equal to then opposite y over hypotenuse 1, which is then y equals sine of 45, and y is again root 2 over 2. We shouldn't be surprised by that because, again, it's isosceles. The two legs are going to be congruent. But our coordinate there is root 2 over 2, comma root 2 over 2. Oops, I'm off the screen. There we go. Root 2 over 2, comma root 2 over 2. Okay. Don't worry, there's only one more in this quadrant, and then 9 more in the other 3 quadrants. We're almost there, guys. Okay, now let's look. So that's the location of the point where found on the 45-degree angle there on the unit circle. Let's do the last first quadrant angle that we need. Okay. What's the next one after 45 on the unit circle? 60. Okay, so there's 60 degrees, which is equal to pi over 3. Don't ask me why I wrote radians first and then this one I wrote degrees first. I have no idea. Okay. Again, the height will be the y-coordinate. This horizontal distance will be the x-coordinate. And we're trying to find that point on the coordinate plane. But wait a minute, we've seen this triangle before. Where did we see it before? In the third degree, right? This is 30, 60, 90. This one is also 30, 60, 90, but their locations are swapped. So x is the short leg here, and what does that correspond to in the original 30, 60, 90 we did? That matches to the what? The y, okay? So the x coordinate here is going to be the y coordinate from here, so it's 1/2. Okay? Likewise, the y is the long leg, which corresponds to x, the long leg here. What was x here? Yeah, root 3 over 2. You're right. Yeah, root 3 over 2. Okay, and so then root 3 over 2 there. Okay. If you don't believe me, you can, pull the triangle out, sketch it, and then do the same calculations we did. Do cosine of 60, you'll get 1/2. Do sine of 60, you'll get root 3 over 2. Okay? So, there's all that. So now if we go to our unit circle paper, we can use this information and put it on our graph. Okay? So did we already have 1, 0 here for the coordinates? Okay, we did do that earlier? Okay, so I already have some of those points, but I don't have, for example, this one, right? So right here, right, 30 degrees pi over 6, square root of 3 over 2, comma 1/2. Okay? 45 degrees, comma, or pi over 4, that is root 2 over 2, comma root 2 over 2. Okay. And then 60 degrees, or pi over 3, that is 1/2, comma root 3 over 2. Question, Ryan? Yes. Okay, and then I put the 1, 0 and the 0, 1 in there too, just for our purposes. Okay, now we did the first quadrant. We only have 3 more quadrants to do, but we can use transformations to help us here. Okay, what kind of transformation can I do to these coordinates to arrive at these coordinates right here? Yeah, a reflection over the y-axis. Okay, so when we reflect these points, over the y-axis, right, reflect them over, all right, what happens to the x-coordinates? They'll become opposites. What happens to the y-coordinates? Nothing, they stay the same. Okay, so all these y-coordinates are going to stay the same. So for example, here at 120, that is a reflection of 60, or pi over 3, over the y-axis here. Okay, so then the coordinate here is just going to be negative 1/2, comma, positive root 3 over 2. For 135, negative root 2 over 2, comma, root 2 over 2. And then for 150, negative square root of 3 over 2, comma, positive 1/2. And then here at 180, well, it's the negative 1, 0. Okay. But now that we have quadrants 1 and 2, what can we do with those quadrants to then get quadrants 3 and 4? Reflect or flip over the x-axis. And when you reflect over the x-axis, okay, what stays the same? X stays the same when you reflect over the x-axis, and it's the y's that will then become opposite. So for example, 210 will be a reflection of 150 over the x-axis here, and so the negative root 3 over 2 stays the same, but now it's the y-coordinate, negative 1/2. Okay, it's opposite. And then here, negative root 2 over 2, negative root 2 over 2, comma, negative root 2 over 2, for 225 or 5 pi over 4. and then -1/2, comma, -√3 over 2 for a 240. 270 is 0, -1. We already had that one there. Okay, so I'll let you guys write that real quick, and then we'll finish off the rest. So I think I can get it squeezed. Yes. Okay. And so then this will be +1/2, -√3 over 2. √2 over 2, comma, -√2 over 2. And then √3 over 2, comma, -1/2. Okay. And there are all the coordinates for our unit circle. Okay. Yes. Yes. So why do we bother filling this out, right? This is a lot of information. It was a lot of work, okay? Very dry. Why do we do this? What's the purpose? Well, let me explain here. Okay, with these coordinates, all right, remember how we first came to understand the coordinates in the first quadrant here, okay? We made these special right triangles, and then we used trigonometry, right? We did cosine of 30, which was equal to x. Y was equal to the sine of 30. And then here, x was equal to cosine of 45. Y was equal to sine of 45. You're starting to see a relationship here between cosine and the x-coordinate and sine and the y-coordinate. In fact, okay, the x-coordinate of any point on the unit circle here is equal to the cosine of the angle. Likewise, y is equal to the sine of the angle. Okay? So for example, if I wanted to know what the cosine of 3 pi over 2 was, I could locate 3 pi over 2 here on my unit circle. Cosine is the x-coordinate of 3 pi over 2. What's the x-coordinate at 3 pi over 2, or at 270 degrees? What's the x-coordinate at the cosine of 270 for the cosine of 270 degrees, or the 3 pi over 2? What is the x-coordinate here? 0. So cosine of 3 pi over 2 or cosine of 270 degrees is 0. If you type it in your calculator, cosine of 3 pi over 2, and you're in radian mode, you get 0. If you type cosine of 270 degrees in your calculator, and you're in degree mode, you get 0. Okay? So this provides us a way to evaluate trigonometry, sine and cosine, without using a calculator. Okay? No calculator necessary, because it's just all here on the unit circle. We have the exact precise values as opposed to those rounded values. Okay? The way your calculator gets those rounded values and stuff like that is actually something you'll learn how to do in calculus. If you take calculus A, B, B, C. If you take calculus B, C, you'll get to see how we do that. Okay? It has to do with an infinite series. We'll talk about series later in this class, but we won't talk about, I'll show it, maybe I'll show it to you, what sine and cosine are as an infinite series, but anyway, there's the information. So what I got for you right now, okay, to help practice just identifying, exact values on the unit circle, I have a coloring activity, okay? If you want to color, you don't have to, okay, but I do want you to answer. So what I've got for you here, for example, is you're going to evaluate all these trig functions. They're all sines and cosines. Okay, so for example, here's sine of 5 pi over 4. Well, sine, remember, is the y-coordinate, and it's sine of 5 pi over 4. So if I locate 5 pi over 4, right here, okay, what is sine? -√2 over 2, the y-coordinate there, -√2 over 2. So, since it's -√2 over 2, what color would I color it? Red. Okay, so this triangle would be colored red. Okay.
Just write the word red.
You don't have. You can just write the answer. I would prefer. Okay, but I do have colored pencils if you want to do the actual coloring here. Okay, It was more popular than I expected it to be with the coloring, so your choice. Okay. Notice for 0, if you get 0, you can do any color, your choice. Okay, 0 is any color, your choice. You do not need to color, but at least identify the quantities, the values, the answers. Okay? Eventually, we're going to get to the point where in our timed quizzes, I'm going to give you things like these kind of questions, like sine of pi, sine of 2 pi over 3, cosine of 3 pi over 4, and you'll be asked to evaluate those, in a certain amount of time. Okay? And I'll show you some strategies to help you with that, rather than just redrawing the entire unit circle. Sine of pi is 0. Don't forget also you have a TenMarks due on Monday. So if you want to work on that instead of this, that's your choice. Okay? What's up?
I have one more left, and I have a question. So,
Oh, no pie. It's not right. I know, but they must learn, Lindsay.